Welcome, everybody. So, in case that you get disconnected or your internet is not working as well, the lecture is being recorded so you can work on the exercise on your own and see it later if needed. All right. So, the first thing is let's go over the problem that we're doing today. So, I'm going to make my screen be presenting. And I don't think I can see the chat. So, if you guys need something, speak up, okay? All right. So what we're going to do today is time and length measurements at very high speeds. So the first thing I'm going to do is tell you about the strategies that we need to do. So when you're traveling really fast, the measurement of length and time intervals depend on which reference frame you're in. So you need to take really good care of the hardest part of solving these problems is making sure that you're working with the right reference frame in whatever information you're given. So let's see, this is the strategy that I would recommend to follow. When you're given some numerical quantity, you need to identify for what observer or reference frame that quantity is given for. And then you have this observer and reference frame, and you give it a letter to determine, to make sure that you have this right. So you would write a letter on the time and such. If you have an exercise where you have time intervals, what you need to do is identify the events that go with that time interval. So if you have questions, just speak up, okay? So you know that two events, like for instance, there's a star supernova happening. That's an event, right? So it does a second pulse. That's the second event. That gives you the two time intervals. And then you have to determine in which reference frame the two events will occur at the same position. So that would give you the proper time. So if there's a proper time for that, for those two events, then you have to have that they're happening at the same position. So this is similar to what we did in one of our first classes. The next thing is you have to identify the distances or length mentioned in the problem or exercise. So you have to determine for which observer the object is at rest. And if you do that, if that exists, that there's a observer that sees the object at rest, that observer is measuring the proper length. Now with that, what you need to do then is use equations to determine. So for instance, if I give you the time interval in one observer and you need it for another observer, you need to translate between the two. And the same thing for the length, right? You have the proper length. Now you have to do the length for somebody that is not at rest with that object. So to do that, you use the following equations and then you translate between intervals or distances. So for instance, if you know the proper time, an observer that is moving with a velocity v, and here's the velocity v, would see it that same time interval that was in the proper time is going to change by this gamma factor. So that means that if in the proper time it was something that was happening in a time interval of 1 second, if the speed is fast enough so that gamma is not 1, then the time interval is going to be increasing significantly. That makes sense, right? That's what this gamma is doing. If you have a length, All right. If you have a length in the proper length, in the when the observer sees this, let's say a ruler that measures 1 feet, if the person is traveling really fast, then you can see an observer that is moving with the speed relative to that object would see that object get smaller. So that means that instead of seeing 1 feet, maybe it's just 10 inches if they're traveling fast enough. And then you use that equation for gamma. So the equation is here. You write the speed in terms of the speed of light. So for instance, if it's 20% of the speed of light, then you have to do 0.2 squared, because the c's would cancel out, and you have 1 minus 0.2 squared. You have to do that, um, and then take the square root and the inverse of it, and then you get the value of gamma. So any questions so far? No? All right. So then let's look at the exercise for today. How many of you have seen this movie? Let me see if I can do the poll. So I don't know if you guys have seen this movie. All right. So it looks like 2 versus 4. So I don't know if you guys would agree, the two of you that watched it. It's a terrible movie. Actually has a very disturbing premise, right? And I don't want to ruin it for anybody else, but I would say you don't need to waste 2 hours of your life watching it, because it's not that good. Um, However, let's see, there's something in the chat. Yeah, it was terrible. So, however, the main thing is that in this movie, they're going in a spaceship to another star system. They're traveling at some speed, then they have some damage, and now the spaceship is malfunctioning. So then Chris Pratt wakes up for some reason. They were all sleeping because they're going to travel for many, many years. Chris Pratt wakes up, realizes he's the only one awake and he cannot get back into his hibernation chamber, and then gets a message of when they could get rescued. So that's how the movie goes. Um, what I wanted to do is look at this from a special relativity point of view and see how it could work. So we're going to have the same idea as there's interstellar travel. We have that the spaceship left Earth some time ago, is traveling towards the star Vega. So when it's traveling, at the beginning of the spaceship is just accelerating, right? So now the main thing is that special relativity doesn't work when you're accelerating. So now for our malfunction, it means that the engine stopped working. So now it's just drifting with a constant speed in the direction towards Vega. So now special relativity is working. And all the equations I showed you before would work. So the chip is sending a distress signal, and the distress signal is a series of pulses sent by the chip at 1 second apart. So it's like a beep, 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 beep that happens every second in the spaceship. Now, that signal gets to Earth. You're the dispatcher on Earth that receives the distress beacon, right? And when they get to you, the distress beacon is coming at you at 2 seconds apart. So there's two parts to this question. The first one is that you're the dispatcher, right? And you need to send a rescue crew, and the rescue crew that you will send needs to know where to catch up with the chip. So you need to calculate the route, and you need to know how fast it is traveling so that they can catch up with it and be traveling at the same speed as the spaceship. So you need to calculate this route. So the most important parameter would be how fast is the spaceship going in the Earth reference frame. And then there's a second part. The second part is that you're the dispatcher, right? So you also need to tell Chris that help is on the way so that he doesn't do something stupid. And the approach to send you get the distress signal, then you start sending your own signal back. The standard approach is that you send pulses that in the frame of reference of the ship are 1 second apart. At what intervals do you need to send the pulses? So what is the interval that you put in the pulses so that they get to the ship and they're 1 second apart? Since it's traveling way faster and the reference frame of it is that it's traveling at really high speed, that means that if you send it at 1 second, over there, they're gonna receive it not at 1 second. All right, so any questions about this and what we're dealing with? So if this was a normal class in person, what I would do is that I would break you apart into groups and tell you to work out the problem and come up with the strategy for it. So what I wanted to do then is to make, we have 1, 2, 3, 4, 5, 6, 7 people. So I'm gonna make breakout rooms. I'm gonna make 2 breakout rooms. You get assigned automatically to them, 3 to 4 in each of the rooms. And then you guys can discuss, and then we come back in 4 minutes to see how to do it, okay? So we'll do that. And then we're coming back in 4 minutes. So you guys can discuss over chat, over video, over voice, whatever you want to do. Questions? All right, so then I'm sending you out to your breakout rooms. And perfect. All right, so Joshua, are you around?
What?
Joshua?
Yes.
All right, so what was the strategy that you guys came up with to solve the first part?
We were going to, so the change in time with respect to velocity, is that 2 seconds?
So, all right, so let me share my screen this way so we can draw, so I can draw on it, okay? And you guys can see my screen, right?
Yes.
All right. So the first thing is that we know, let's
Can you
see.
write down the equations again, please?
Yeah. Let me do that. So the most important equation would be the gamma one. And this is the one that goes with the square root on the bottom. All right, so then the one that we need is the one that the velocity interval, the time interval versus the proper time interval. So like I told you, the most important thing is to figure out which of them is the proper time interval. Okay, so let me see. Let me do we have two reference frames. So the first one is the Earth reference frame. Let's write what we know, okay? And then Joshua, you're helping me, okay?
Okay.
So in the Earth reference frame, we have first that Earth is right here. And for Earth, we have that there's an event. Well, here's the Earth. In the Earth reference frame, there's no velocity, right? But then there's the spaceship that looks like this. And event one happens. And then event two happens over here. So then event one is the first pulse. And event two is the second pulse. And we know that the chip is moving with a velocity in that direction. And this is the velocity in the Earth's reference frame of the chip. So you see those are the letters that I have to identify, right? All right. So then what's the next thing? Do I know here how much distance passed between event one and two? Joshua?
No.
All right. Do I know how much time passed between event one and two?
From the reference frame of the Earth,
Right.
2 seconds.
Actually, no, because what happens is that event one, let me draw it like this, right? Event one is this pulse coming out and being seen here. Okay, and then event two, so this one in orange right here is event three. That's where you get it. And then event two is when it happens on the spaceship. But then event four is going to be when it reaches Earth. So we have to be, it's not exactly the same thing, right? It's not the 2 seconds. Does that make sense to everybody? So in the Earth reference frame, how much time passed between event 3 and event 4?
Is that 2 seconds?
That's the 2 seconds.
Okay.
And then we also have something that we know. What is the space-time interval what is the space interval between events 3 and 4 on the Earth?
0.
0. And then I guess, hold on. Do I want to do, yeah. So let me do it this way. So this is 3 and 4 on the Earth. So this one is 0. This is on Earth. This is on Earth. And this is on Earth. All right, so we have all that, right? Now I'm gonna go with somebody in the second room. So how about John? Are you there?
Yeah, so I think we said like send it like half a second earlier.
All right. So what is the strategy that you're taking, right? The first thing was how fast the chip was going, and the second one you're telling me how much time apart you need to send them so that they get at the 1 second. Is that what you're saying? Half a second early?
Yes.
All right. So actually, that's correct. So, but let's draw this the whole way, right? We have two events happening, event 1 and an event 2. The first one and the second one, do they happen in the chip reference frame? Is there a separation in space between event 1 and event 2? John?
Yes.
Or are they happening in the same place? Because it's happening out of the chip, right?
Oh yeah.
Is it 0 or there's a space separation?
So there's no separation.
All right. How about the time separation?
There is time separation.
And how much is that?
Was it 1 second?
Exactly. All right, so now we have that 1 second. And then if we look at the Earth, the idea is that the Earth was right here when event 3 happened. And then it was over here when event 4 happened. And in this frame of reference of the spaceship, it's not the spaceship that is moving, but rather is the Earth moving in that direction. And this would be the speed that the Earth is moving away from the spaceship and is in the opposite direction. So the velocity is opposite to what we had before, right? But it's the same magnitude. So then I have the time interval between events 3 and 4 in the spaceship. We don't know that. And do I know this space interval between the space between event 3 and 4, John?
I don't know.
No, that one you don't know either. All right, with all of this information, the first question is, what do you need to do? You have to relate the time differences between pulses emitted in one reference frame and pulses received in another reference frame. So we have event 1 and 2, and we have event 3 and 4 in the reference of the Earth. All right.
Just a quick question. I kind of got lost halfway through. A and B, are we answering the A question and then the B question, or are we talking about the two reference frames?
So we need to talk about first set up the whole problem, and then we can answer question A. And then question B, room 2 got it right. but I don't know if they did it through algebra or through guessing. So you guys can tell me.
So the A, now what we're writing, we wrote A, Earth reference, B, ship reference. That
Oh,
is
sorry.
not answering
I
question A
guess
and
that's
B.
what is confusing, right? So this is just the reference frame A and B are not related to problem A and B. Sorry.
Okay,
Just
yeah,
so
that's
that I
better.
have the setup complete.
Thank you.
All right. So then the first thing is we need to calculate. All right. So we have the plan that we need to devise is the following. We have, now I need to make a space. All right. So this is where I'm writing things on the bottom. So here's the first thing that I know how to get. I need to know this time over here, which I don't know, right? But I know that I can relate it through this in the spaceship between 1 and 2. So the first thing is for you guys to calculate gamma, the Lorentz contraction factor. So I don't know if somebody wants to do it or if somebody has already done it. And I'll wait for you guys to do it. But once you have that value, then you can figure out this 1 second and put it up here. Okay? So do I have a volunteer working on it already? Christian, do you have it?
Um, for gamma, do we know what the velocity is?
No, that's a tricky question. That's what we actually don't know, right? Because if we knew it, then we know exactly everything. But we have to come up with something that is written like that. Okay? So it's not, that's the exact thing that we need to figure out. How do we relate this to this? Is just by doing this transformation, and we need this gamma to do that transformation. So we cannot just stick it in there. All right, so then let me do.
How do we know which one is the proper one?
All right, so that's a good question. Here, we have that the two events are happening in the same position, right? So for that observer, the two events occur at the same position. So that means that that gives you the proper time. So this one right here gives you the proper time. Okay. All right. So then let's write. The thing is that I don't have enough space and I don't want to erase anything. All right, let me go to another piece of paper here, okay? So in the Earth reference frame, the time interval it takes for the signal to reach Earth is the distance from the chip. So first, we have on the Earth between 3 and 4. This is the same as the time that event happened, 4 happened minus event 3 happened. So that's a time interval, right? And what this is the time that event 2 happened in the Earth reference frame plus the change in position, no, the position that event 2 happened divided by the speed of light minus, and let me just put it like this because they're two different events. When event 1 happened in the Earth reference frame, plus the position of the spaceship in event 1 in the Earth reference frame divided by the speed of light. So let me come back to that equation, but looking at it here. So we know that event happened, and this is that event 1, and this is event 2. So when this signal travels, it travels from here to here. That's clear, right? And when this signal happens, it travels from here to here. So it's a different time, it's a different space interval. Does that make sense to everybody? That's why we have a new, we have to have this one and this one. They're not happening at the same position in the Earth reference frame. Any questions about this?
Can you repeat again how you got to this, to T4 equals T2 plus X2?
Right.
Listen?
So yeah, let's go back over here. All right, so we have event 2 happens, and then that signal is traveling at the speed of light and reaches Earth, and that happens to be event 4. Right? So event 4 is event 2 happens after event 2 when the signal is traveling all of this distance and gets to us. So that's where I'm getting so that's how I'm getting that event 4, right? Is event 2 plus this distance divided by, so that's distance divided by speed, so it gives you another time. The time that the signal took to get to us. Does that make sense now?
Yes, thanks.
All right. So now that we have that, I can rewrite this to things because this one minus this one, what is that? That's delta T on Earth, 1 and 2. And then this one minus this one, well, that's just delta x on Earth between 1 and 2 divided by the speed of light. So now we know that we can relate the distance that the spaceship moves, and we know that distance that the ship moves between events 1 and 2 is the speed. So then I have the following equation. This guy is moving with this speed times the time interval between those two events, which is this, right? So I can use this. So does this part make sense?
Why would it be in Earth's reference frame and not in the ship's reference frame?
Oh, because in the ship's reference frame, the spaceship is not moving, it's the Earth that is moving. So in that ship reference frame, it would be like finding this guy. But then we have to relate those other two events when event 3 and event 4 reaches Earth. But here we don't know this one. But we can relate it now with this equation to the two intervals. So hopefully
Are
it
the
makes sense.
two VS's the same,
Yeah.
equivalent?
They're the same because one is moving with respect to the other one, right? They're the same magnitude, except one is going, you're seeing it moving away from you, and then the people in the spaceship they're seeing Earth moving away from them, but it's just with the same speed that they're moving away. So now I can relate the time intervals and the speed to the distance traveled by the ship in the Earth reference frame. So now that I have that, I can stick that back over here, and I would have that this interval is equal to the same that I had before. And now I have to add my velocity or speed, sorry, then the time interval on Earth 1 and 2, and then divide this by c. So you see that we have the same delta TE on both sides, so I can take it out and do this algebra. And that gives me 1 plus BES divided by C. All right, any questions so far? So that's just algebra, right? Okay, so now I need to do a trick. Let me go back over here. So I know that the Earth frame of reference interval between 1 and 2 and the spaceship frame of reference are related by gamma. So I'm going to use that equation over here. And I have that, let me see. Yeah, so this one, this is the equation that I have written before, is related to this one, right? Those two are related. So now I can write that delta T E 34 is equal to gamma delta T spaceship 1, 2, and then 1 plus BES divided by the speed of light. So now the trick is to rewrite this alpha, this gamma, which is the 1 over 1 minus b squared over c squared there. And you see that this speed is the speed ES divided by c squared. And do the algebra with it. So this is going to be the first part of the algebra that you need to do, a little bit more difficult algebra. But you can now solve because let's go back over here. We're looking at the time interval on Earth between events 3 and 4. Time interval on Earth between events 3 and 4. We know that one. And you know this one. You know this one, right? So now you can solve for this velocity. That's your only unknown, and you have one equation. You just have to do a little bit of algebra. Questions?
So we're replacing the gamma with that 1 over square root and then solving for velocity.
Well, not replacing, right? Because that's the meaning of gamma, but you're just solving for velocity. You have a square root on the bottom, and you have a velocity on top, and then you do some algebra or however you want to solve it, and you should be able to write to extract what is the velocity out of all of that from algebra.
Okay.
Okay? So once you figure all that out, you can get what is the time So once you have those, you can obtain velocity. So that's your homework. And then once if you have that velocity, you can say how fast is traveling the speed of the ship in the Earth reference frame. And then the last thing you can do is just, and I don't know how you guys did it, John, but you got it right, that your interval has to be half a second, so that when they get to the chip is working at 1 second intervals. All right. So that would be what you do for your homework. And then I'm going to open up assignment page for you guys to do. Any questions? So this is clear. So if you guys want to work together with the people in your rooms, I don't know if you want to share information between you or something like that in solving the problem. I'm okay with working together. And just let me know if you were working with a group or not. Okay? You guys want to have the chat room open again so that you can share your information? You can send yourself the data on the chat if you want. All right. So that brings us to the end. Stay warm.